Okay, so hopefully you figured it out. I'm going to have to go way down here on the blackboard. What do we got? Well, A top left is A00, A01, A10 transpose alpha 11. A bottom left, when we move forward, becomes A20, A21. A top right becomes A02, A12 transpose. And then finally down here we got A22. And because we have now done some more computation, LU top left becomes LU00. Below here we just have L10 transpose. Above here we have U01. On the diagonal we get the diagonal element of U, epsilon 11. That's the top left part. Down here we still have A20 hat, A21 hat. Up here we have A02 hat, A12 transpose hat, and A22 hat. Okay, that's that part. And now comes the tricky part. What about L top left times U top left? Well, that is L00, L10 transpose 1, because we know it has to have a 1 on the diagonal, times U00, U01, 0, epsilon 11. And that must be equal to A00 hat, A01 hat, A10 transpose alpha 11 with hats. Okay, well hopefully it fit on your piece of paper better than it fit for me. What's now the next question? Well, how do we go from this state to that state? Okay, I've created some space. Now let's just think this through. A0 should have L and U00 in it. A00 already has that in it, so nothing needs to happen to that variable. These 5 pieces of the matrix have this in it and must have that in it, so those obviously don't need to be updated either. So far so good, right? So really it is these pieces here that somehow have to be updated from having not changed at all yet to having pieces of L and U in it. Okay, so the first thing we know is A01 must be somehow updated, A10 transpose must be somehow updated, and alpha 11 must be somehow updated. And how should these be updated? Well, the key is right here. Okay? Because this really relates how pieces that we already know, this, and this, relate to pieces that we want to compute. Okay? Now, we know that A01 should be updated with U01. And then A10 transpose should be updated with L10 transpose. Lambda 11 should become epsilon 11. But that doesn't help us much because we don't know what those are. If we now multiply this out, what do we get? Well, by now hopefully you're getting really good at partition matrix multiplication. It's this times that plus this times that. So we get L00 times U00. We get this times that plus this times that. So that is L10 transpose times U00. We get this times that plus this times that. That's L00 times U01. plus 0 times that. And then we get this times that plus this times that. That is L10 transpose times U01 plus epsilon 1, 1. Okay. But we know that that must be equal to A00 hat, A10 transpose hat, A01 hat, alpha 1, 1 hat. Okay? So what do we know? Well, first of all, we know that L00 times U01 must be equal to A01 hat. Where can we write that? Well, we'll write it here. We know that L00 times U01 is equal to A01 hat. But wait a minute. We know L00. It's already been computed and it has overwritten part of A. Okay, so this we know. It's a unit lower triangular matrix. A01 we know. It's the original contents of A01 and we know that it's currently stored in A01. So what we conclude from that is that we need to compute U01 that satisfies the lower triangular system L00 times U01 is equal to A01, where we can take the hat off because we know that that actually is stored in A01. Okay? That's good news, because if you took a linear algebra course, you know that solving a lower triangular system is easy. It's bad news because we haven't developed a function to do so. Okay. Well, let's just assume that we know how to do this, and let's actually, although we're not going to compute it this way, let's denote it by L00 inverse times A01. Okay, because if we had the inverse of L00, then we could multiply both sides by the inverse, and we would get this right here. This is a statement of what needs to be computed. It's not actually how we would compute it. All right? So maybe you're catching on now. How do we compute L10 transpose? Well, we know that L10 transpose times U00 is equal to A10 transpose. You know what U00 is, you know what A10 transpose is. Well, we know we want to compute with A10 transpose hat, but we know that's stored right there. Okay, well, we can multiply both sides of this with the inverse of U00, and then we would find that this is equal to A10 transpose times U00 inverse. Now, this brings up an interesting sticky point. We know that a unit lower triangular matrix has an inverse, so this operation is legitimate. This particular operation, maybe not, because if there's a 0 on the diagonal of U00, then the inverse would not be well defined. So obviously we're only going to work with problems for which this doesn't break down. Okay? The theory behind all of that is a different matter. It's another course. Alright, so now we have these two operations. We'll revisit later how to actually compute this, but we can move on. Okay, what's left? We need to figure out how to compute epsilon 1, 1. And you kind of see the pattern. You look down here, you see that it's equal to that. We know alpha 1, 1 hat, and we know it's stored in alpha 1, 1. By now we know L10 and U01, because those have now overwritten their counterparts in A. In other words, we know that L10 transpose U01 is equal to epsilon11, sorry, plus epsilon11 is equal to alpha 11 hat. This we know, this we know, this we know. So we can bring this to the other side and say, oh, epsilon 11 is this right here. You take the dot product of these pieces and subtract it off. Ah, but this here is stored in alpha 11. And this L10 transpose is stored in A10 transpose. U01 is stored in A01. So what we need to compute is alpha 11 minus L10 dot product with U01. Oh, except stored in A10 and A01. And what we've just done systematically is come up with what the update step should be.